So you're going to a restaurant with another person, and after you're done eating, you need to pay. Neither of you want to pay, and you don't want to split the bill, for some reason, so you decide on some fair way to decide who should pay, like rock, paper, scissors, or flipping a coin. Whoever loses the chance game, whatever that may be, has to pay. Seems fair, right? Well, what if you had 4 people? Flipping a coin twice has 4 total results, so you can assign one of them to each of the people, and whichever person's assigned result is flipped has to pay. Likewise, if there are 8 people, you flip the coin 3 times, and for true to the n, you flip a coin n times. But what if there are 3, 5, 6, or any non-power of 2 amount of people? What probabilities can coin flips make? So instead of focusing on everyone in your party at once, which could be a bit complicated, let's just try one person. If you have n people, you want this one person to have a 1 in n chance of being selected. So the 2 outcomes for this person are yes, meaning they're selected and have to pay, or no, meaning that somebody else has to pay. What we want is some system of coin flips such that the probability of going to yes is 1 in n. Now I should probably introduce some notation. I'll be calling a system which has an A in B chance of going to yes an A over B gate, similar to a logic gate but randomly chosen. And to draw out these systems, I'll be using Markov chain diagrams. You can think of these like a marble going through tubes to different stations. In this case, if you're at A, there's a 1 in 2 chance of going to B and a 1 in 2 chance of going to C. If you're at B, then you have a 2 in 3 chance of going to C and a 1 in 3 chance of going back to A. And if you're at C, then you have a 3 in 5 chance of going to A and a 2 in 5 chance of going to B. The only thing that determines the probabilities of going down each of the tubes is the station the marble is currently at. In this special scenario with only coin flips, each flip has 2 equally likely outcomes, so each state or station has exactly 2 other states to go to. The only exceptions are the ending states, like yes and no. We'll only be using yes and no here, but maybe if this gets, 50 likes or something, I'll show some multi-end gates. Since there are only ever 2 roots and they're always equally weighted, we don't need to label the probabilities of each root. They're always a half. We'll denote the starting state by a blue circle around it. I call these specific Markov chain diagrams coin diagrams since they exclusively use coin flips. Now that that's out of the way, we can apply this to a case we already know, like n equals 2, which is a 1/2 gate. This one is pretty easy. We have a state that goes to yes and no. There will be a 1 in 2 chance that it goes to yes, just like we wanted. Just so you can get used to this, we'll try n is 4, which is the 1/4 gate. Since we want a 1 in 4 chance of yes, we can chain together 2 1/2s like this. So the only route to go to yes is here, which has a 1 in 4 probability of happening. And if you want 1 in 8, just add another 1/2 like this. Okay, now I hope you're used to these because we'll use them quite a bit. So let's dive into n equals 3. And it's a bit of a puzzle to think how we can make a 1 in 3 gate. It isn't a clean power of 2, so it isn't obvious how to do it with a finite number of states. And it's completely possible. So I want you to figure out how to get a 1/3 gate. I'll give you a hint if you're stuck right now. It takes only 2 states other than yes or no to make the 1/3 gate. Maybe you're still stuck, so here's another one. You'll need to loop the states in order to make it work. Okay, before I give you the solution, I'll show you something that will make it make sense. So you may have heard a puzzle that goes something like this. There's a bag with 2 balls inside. Each ball is either red or blue. You learn that at least one of the balls is red. What is the chance that both of the balls are red? Surprisingly, the answer is 1/3. Before you took out the first ball, there were 4 equally likely possibilities. 2 reds, 2 blues, red-blue, and blue-red. By taking out a red ball, you gain information. You know now that the possibility 2 blues is impossible because there's at least 1 red ball. Now the only cases are 2 reds, red-blue, and blue-red. Now it's clear there's a 1 in 3 chance of getting a red. The other 2 cases would result in the other ball being blue. And look at that, we just made a 1 in 3 probability out of a binary outcome, red or blue. So can we apply this logic to coin flips? Well, yes. What we did with the balls in the bag was removing a possibility from the space of outcomes. If we could make one of the roots impossible and make all of the roots equally likely, we would get a 1/3 gate. But you can't just remove a possibility out of a coin flip like that. If you got rid of this arrow, it just becomes another 1/2 gate because not all the combinations are equally weighted. But what you can do is to make one of the possibilities restart the process. This way, it's still possible to go down that route, but it's impossible to end with that result. Now, there's a 1 in 4 chance of yes, a 1 in 2 chance of no, and a 1 in 4 chance of re-rolling the process. It's impossible to end on that reroll, so that quarter doesn't really exist. It's removed from the space of ending possibilities. So the yes to no ratio is now 1 to 2, so yes must have a 1 in 3 chance of being selected. We've created a 1 in 3 gate. Try flipping your own coins to verify this for yourself. Cool. Now that we have a 1 in 3 gate, what other probabilities can coin flips make? Well, I'm about to show you how to make any, and I mean any, rational probability. Start with the beginning state on top, and split it into 2 more states evenly. Split those into 4 states total and keep doing this until you have enough endings. How much is enough endings? Say we want to find a over b, where a and b are positive integers. You'll need to double the endings until there are at least b of them. For example, if we want a 5 and 19 gate, we'll need to double the arrows 5 times so that there are 32 straight arrows. Where do these arrows go? Attach a of them, in this case 5, to yes. Attach b minus a of them, in this case 14, to no. And attach the rest of them back to the beginning state. Some of the states guarantee going to one place, so you can get rid of them entirely if you want. The probability will stay the same because it doesn't actually split between 2 outcomes. They don't even make a distinct choice. Anyway, this works because it rerolls all the times it wouldn't be out of b, or 19. Thus, only 19 or b outcomes are possible, and a of them will result in yes. Therefore, we have an a over b gate. It doesn't matter what rational number you pick because it always narrows down the probability to exactly a over b. So, because there's a method to generate all rational probabilities, it is possible to do so. Now, I don't have any actual proof of it, but I do suspect that irrationals aren't possible to make with coin flips. Assuming a finite number of states, I think you can only really make rational probabilities, but the looping throws things off, so I really have no idea how to prove this. However, it is pretty obvious that the method that I showed before with a giant tree is not optimal at all, in the sense that it has too many states at least. For example, a 1 in 5 gate with this method gets you anywhere from 3 to 7 states, besides yes and no. Depending on which arrows you pick to go where, it can have a varying number of states. But we can chain together a 1/2 and a 1/3 to make a 1/6, and then if you loop back the 1/2 instead of going straight to no, you can turn this into a 1/5 by removing a 1/6 from the sample space of endings. Now, we have a 1/5 gate with only 3 states. By the way, when I say state from now on, I'm referring to states other than yes or no. Although yes and no are technically states, it's easier to consider them more as ends, plus it's easier to write out a formula for this, which I'll show later. So this 1/5 gate basically has 3 states in it, which is the least possible. And the reason that 3 is the least possible is that every additional state can only reduce the probability by at most a factor of 2. With only 2 states, the lowest possible probability would be 1/4, so a 5th requires at least 3 states. Now it's a pretty fun puzzle to pick a probability and try to minimize the number of states in its gate. I actually encourage you to try putting some gates together and seeing what you can find. In fact, if you make a table of the least number of states possible in a 1 over n gate, you'll see an interesting pattern. There will always be a gate with a number of states exactly equal to the theoretical lower bound. By the way, the function to describe the theoretical lower bound is the ceiling of the log base 2 of n, which I'll denote as f of n. The function essentially describes the order of the least power of 2 which is greater than n. For example, f of 5 is 3, and f of 129 is 8. But does the pattern continue for very high values of n? Well, I have a very interesting proof that a 1 over n gate with exactly f of n different states is always possible. It goes like this. Look at a very specific family of gate structures with exactly m states. They consist of a long sequence of m states, going from the starting state to yes. The starting state connects to the next state in the sequence and no. Every state following this connects to the next state in the sequence and one of either the starting state or no. These m-1 different states have exactly 2 different types. Therefore, there are exactly 2 to the power of m-1 different gates of this type with m states, and we can determine which probabilities each of these gates makes by working backwards from the end. We'll begin at the end of the chain where the current denominator is 2, and as we go backwards in the chain, say the current probability is 1 over k. Now the denominator is k. If the second arrow connects to no, then it takes an extra coin flip in order to reach yes. The current probability is now 1 over 2k. However, if the second arrow connects back to the start, then the current probability is halved. The arrow that would end the sequence completely simply restarts the process. So we've actually removed one equally likely ending from the sample space. So instead of 2k possible outcomes, there are now 2k minus 1 possible outcomes. Every state modifies the denominator of the current probability as either 2k or 2k minus 1. Now let's look at these operations in reverse. Say you're given a denominator n between 2 to the m minus 1 plus 1 and 2 to the m. If n is even, the last operation must have been doubling, since that's the only way to make an even number. We undo it by dividing by 2. If n is odd, then it must have been 2k minus 1, by the same logic. Now we've uniquely determined a previous denominator, and if we continue to repeat this, matching each operation with whether it's even or odd, we can uniquely match each n in that range to one of these gate structures. Now notice what's happening. Every denominator has exactly one possible parent, so in an induction sort of way, we can uniquely match it up to one possible gate. And now to finish off, there are 2 to the m minus 1 different denominators in the given range. And we also know that there are 2 to the m minus 1 different gates with m states in them. So every gate makes a unique probability denominator, and we know the range that these denominators are in is 2 to the m minus 1 plus 1 to 2 to the m. This is also the range of numbers such that f of n equals m. So the least number of states in a gate is the theoretical minimum, and with that is obtainable, which is f of n. F of n also has a nice relation to binary. F of n plus 1 is the number of bits or digits required to express n in binary. Also, if you want to make any 1 over n gate, here is a neat trick related to binary. Make the sequence of states and connect the other arrows in this way. An arrow that loops back is a 0, and an arrow that goes to no is a 1. Take n minus 1 and convert it into binary, then go through the bits in order. For example, that 1/3 gate leaves 1 and 0, which do match the states we had in the first gate. Try this on a higher order gate. And I'll leave it up to you to think about why this might be, and the big reason of it is how we constructed the probability from this method in the sequence. By the way, as I'm editing this video, I still can't prove that irrationals are impossible, but if one of you can, I really would love to hear it in the comments. Anyway, that's basically all I have about these coin diagrams. Thanks for watching, and take care.